Imagine this. You're just going about your day, maybe on a video call with headphones on, and suddenly, bam, a piece of the cosmos, billions of years old, rips through your roof, your HVAC system, and punches a hole straight into your concrete floor. It's an unexpected, almost unbelievable event, right?
Yeah.
You might think we understand everything there is to know about such a cosmic impact, but what if the most profound insights lie, well, in what we can't hear?
That's precisely the starting point for our deep dive today. We're focusing on the remarkable case of the McDonough meteorite. This wasn't just any space rock. It made a very dramatic entrance into a home in Henry County, Georgia, back on June 26, 2025. And what truly sets it apart is its incredible age. It's estimated at 4.56 billion years old. That makes it a staggering 20 million years older than Earth itself.
Wow, older than Earth.
Yeah, and it represents the 27th documented meteorite in Georgia and only the 6th witnessed fall, so truly a rare and significant event.
Okay, so our mission for this deep dive is to look beyond, the immediate spectacle and the sound of the impact from this ancient cosmic visitor. We're here to explore a really fascinating question. Could meteorites be creating subtle, maybe inaudible ripples within Earth's delicate, frequency-based systems? What are we fundamentally missing? Because we're only listening with human ears. All right, let's unpack the dramatic entry of this McDonough meteorite. Though it was roughly the size of a cherry tomato, it certainly packed an incredible punch. Accounts describe its journey. It tore through our atmosphere at supersonic speeds. We're talking over 1 kilometer per second.
Fast, yeah.
Then penetrated the roof, an HVAC duct, and even the concrete floor of a home, pulverizing parts of the flooring into dust. That's an astonishing amount of energy for something so small.
It really is. And while there were no electromagnetic signatures like gamma rays or radio waves publicly reported from this event, researchers primarily focused on the kinetic energy, the sonic effects, and the direct impact dynamics. The homeowner vividly described the sound of the impact as startling and immediate, akin to a close-range gunshot.
A gunshot.
Yeah. Researchers hypothesized they heard 3 simultaneous effects: the collision with the roof, a tiny, localized sonic boom from its atmospheric passage, and then the final impact with the floor. Kind of all at once.
Right. And the scientific effort surrounding this event, it sounds really dedicated. University of Georgia planetary geologist Scott Harris is conducting ongoing simulations, you said, to estimate the entry velocity and trajectory.
Exactly. That work is crucial because it helps model the immense energy transfer that occurs during an impact like this. These simulations are part of a broader effort to understand how Earth might respond to larger incoming space rocks.
Makes sense. And you mentioned people can actually see a piece of it.
That's right. For those of you in Georgia, a piece of the McDonough meteorite is on display at the Tellus Science Museum in Cartersville. It's there alongside other significant finds from the state's meteorite history. Pretty neat.
Okay, but this immediately prompts a critical question, doesn't it? If our primary focus is on what's visible and what's, directly audible to us humans, what about the vast spectrum of frequencies we can't perceive?
Exactly. Humans typically hear sounds between, 20 hertz and 20,000 hertz, give or take. But Earth, as a complex system, it experiences frequencies far beyond that range. It sort of listens differently.
And this is precisely where the research points to a critical gap, isn't it?
Yeah.
Despite the intense focus on this event, there's no publicly reported data for those crucial inaudible frequencies, like infrasound, which is below 20 hertz, or ultrasound, above 20 kilohertz, specifically recorded from the McDonough meteorite itself. Why is this so important?
Well, what's fascinating about these inaudible frequencies is what they could reveal. Infrasound, for instance, it can travel incredibly long distances. It's widely used to detect everything from volcanic eruptions and nuclear tests to large meteor entries.
Like that Chelyabinsk event in Russia.
Exactly like the Chelyabinsk event in 2013, a prime example. Ultrasound, on the other hand, might be generated during a meteorite's fragmentation or through material resonance, especially when it hits solid surfaces like, say, concrete.
Okay, so if we could measure them.
Right. If measured, these types of signals could provide vital information. They could help us identify a meteorite's material composition, understand how shockwaves propagate through different media, or even detect electromagnetic emissions from the ionization during its atmospheric entry. Lots of potential data there.
But that's the key point, isn't it? These signals just go unnoticed unless researchers are specifically equipped and actually looking for them.
Precisely. It requires specialized sensors and a focused effort.
And the homeowner in this case, she was wearing headphones during a Zoom call at the time, so that any subtle or high-frequency tones, even if they were present, would have gone completely undetected by human ears.
That's a perfect illustration of the challenge, yeah. Now, if we connect this to the bigger picture, you're tapping into a really profound aspect of space physics. See, in the vacuum of space, traditional sound waves simply can't propagate. They need a medium, right?
Right. No air, no sound as we know it.
But space is far from silent. It's incredibly rich with electromagnetic waves, plasma oscillations, all sorts of things. In fact, NASA routinely converts these electromagnetic signals into audible frequencies. It's a process called sonification.
Sonification.
Yeah.
Like making space sing.
Kind of, yeah. It helps scientists literally hear space phenomena like solar flares or planetary magnetospheres. It translates the data.
That's incredible to think about, that space isn't truly silent, just inaudible to us
Yeah.
until we, well, translate it. So a meteorite like the McDonough one arriving here, it's truly crossing a very clear boundary, isn't it, from one soundscape into another?
Absolutely. As it transitions from that vacuum into our atmosphere, where sound can propagate, that's exactly where things happen. Shockwaves form, ionization trails can emit electromagnetic pulses, and fragmentation events might produce those elusive infrasound or ultrasonic vibrations we talked about.
Which brings us back to that critical question. Could residual vibrational energy from its incredible journey through space, or maybe the electromagnetic interactions it undergoes upon entering our atmosphere, could that actually manifest as these non-audible frequency signatures?
That's the core of the speculation.
So we're really asking, what are we missing? Because we're only listening with human ears. So if we accept that meteorites might be generating these unseen ripples, it naturally leads to a pretty profound thought experiment. Think about how strict we are with biological imports, right? You can't bring certain plants, animals, or even soil across borders sometimes without risking ecological imbalance.
Sure, invasive species are a huge concern.
Exactly. Because foreign organisms can disrupt native ecosystems.
Yeah.
So apply that logic, metaphorically maybe, to meteorites. They are extraterrestrial objects.
Fundamentally extraterrestrial, yes, often containing minerals and isotopes not native to Earth. And one key concept that emerges from this line of thinking is that their vibrational signatures may be entirely alien to Earth's existing tonal landscape.
Alien vibrations.
Yeah. Now, this is entirely speculative at this stage, we should stress that, but it raises the question, if those vibrations were to interact with Earth's acoustic ecology, its own sort of vibrational symphony, could they affect things? Maybe animal behavior, perhaps even subtle shifts in local geological resonance.
Okay, so this idea of alien vibrational signatures impacting Earth's tonal landscape, it definitely pushes the boundaries. Some might just dismiss it, say it sounds like science fiction. What would you say is the scientific basis, however sort of nascent, for even asking these kinds of questions about potential tonal imbalances? Is it just a lack of data, or is there something more?
It's primarily the lack of comprehensive data, coupled with our understanding of complex systems and wave interactions. We know different materials resonate at different frequencies. We know energy propagates in waves. And we know current planetary defense strategies primarily focus on trajectory tracking, impact modeling, and material analysis of incoming objects. Things we can see or predict physically.
Right, the kinetic stuff.
Exactly. But what if we added multi-frequency monitoring listening across the spectrum to this already crucial work?
That could be another essential layer, couldn't it? Both for how we protect Earth and maybe just how we understand it. Imagine using infrasound arrays to detect incoming objects before they're even visible.
Potentially, yes, for certain types or sizes.
Or analyzing their ultrasonic and electromagnetic emissions to classify a meteorite's material composition from afar. That seems powerful.
It could offer clues, definitely. We could even monitor post-impact resonance to assess any potential ecological or geological effects, however subtle.
So this multi-frequency approach, what could it really deliver?
Well, ideally, it would allow for earlier detection systems by identifying unique signals that current methods might miss entirely. It could also lead to improved impact modeling, feeding vibrational profile data into the models. Better material classification, potentially more accurate threat assessment, maybe even helping distinguish natural objects from, well, something truly anomalous or artificial way down the line.
That's a big leap.
It is, but the principle is sound.
Yeah.
Ultimately, it's about integrating sophisticated multi-frequency sensor arrays and probably using AI or advanced algorithms to correlate that diverse data for real-time alerts and analysis. We'd need smart systems to handle it all.
So the McDonough meteorite, it may have been small, just a cherry tomato-sized cosmic impactor. But its implications, when you start thinking this way, they feel massive. If we start listening beyond the audible, truly tuning into the full spectrum of frequencies, we might just uncover a hidden layer of planetary interaction that's been right under our noses, or rather, just outside our hearing range.
Exactly. This kind of thinking, this broadened perspective, it could fundamentally reshape how we think about space,
Right.
our own planet Earth, and the incredibly fragile, complex balance that exists between them.
So what does this all mean for you, the curious learner tuning in? It really is time to ask, are we missing something critical in our understanding of these cosmic visitors, simply because we haven't yet learned to listen deeply enough across all the frequencies?
Let's lean in and explore. It's a fascinating frontier.